Good morning, folks, and welcome to day 2 of Bravo AP Chemistry at Home. Morgan here, and we are going to be talking this morning about some mathematics involved in doing acid-base titrations. So what I want to begin with is the scenario that we have a burette and that we have a Erlenmeyer flask, and the Erlenmeyer flask contains 100 milliliters of 0.10 molar HCl, and we're going to titrate it with 0.1 molar NaOH. We're going to calculate the pH each of the steps along the way. So what is the pH when we have added no sodium hydroxide? The initial pH, well, this is a strong acid. pH is just going to equal the negative log of its concentration, which is 0.10, which means we get 1.00 as the pH. And that's assuming we're paying attention to sig figs, 2 places after the decimal. Now, from this point forward, what we have to realize is that the NaOH that's added is going to consume some of the HCl that is present. So how much H plus from the HCl do we have to begin with? The H plus equals its molarity times its volume, and that's going to give us millimoles. So we have 0.10 molar times our initial value of 100.0 milliliters, which means we're going to have 10.0 millimoles of H plus present. Now, when we add 15 milliliters of the sodium hydroxide solution, that's going to be 0.10 molar times 15 milliliters. And that's going to equal 1.5 millimoles of OH minus that has been added. So the H plus reacts with the OH minus, it forms H2O, the amount of H plus is going down, it's a complete reaction here, and that's going to give us 8.5 millimoles of H plus left over, and that is in a total volume of 100 milliliters plus 15, which is 115.0 milliliters. The milli cancels the milli, and we now have molar, and this is 0.0739 molar. So pH equals the negative log of the 0.0739 molar, and that equals about 1.13. Now that actually makes sense to us. We're adding base, we're consuming acid, and the pH is going up. Okay? So now, this time, we have added 35 milliliters of the NaOH. Now that's going to correspond to 3.5 millimoles. And what that's going to leave us with is 6.5 millimoles of H plus. So 6.5 millimoles divided by, now let's do some math here. We got 100 mils plus 35, 135.0 milliliters. Boom, boom. And if my calculations are correct, that's 0.0481 molar H plus. pH is the negative log of the 0.0481, and that's going to end up equaling about, call that 1.31. 2 sig figs is what I think we can get away with because of the 0.10 molar and 0.10 molar. So we had originally 10 millimoles of the H plus. We're adding 5 millimoles. OH minus, we are halfway through. we have 5.0 millimoles. H plus left over. Let's get an L in there. All right. So 5.0 millimoles divided by 150.0 milliliters. Milli cancels milli. And in this case, 0.0333 molar H plus. pH is the negative log of 0.0333, and in this case 1.48. The pHs are going up as I add base. This is something that makes sense to me. I think we're in good shape. 10.0 millimoles minus 9.9 millimoles this time. That's only going to leave us 0.10 millimoles. Really just 0.1 if we're paying attention to sig figs. So 0.1 millimoles divided by the 199.0 milliliters. Milli cancels milli. And that's 0.0005 molar. The pH equals the negative log of 0.0005. And that equals about 3.30. It's going up pretty quickly right now. We saw that in yesterday's lecture, looking at the titration curves. Okay? Now, at the equivalence, when you have a strong acid, strong base titration, you have used up all of that original H plus. Moles of acid is equal to moles of base. And in this case, the pH is equal to 7. Okay? The conjugates of the strong acid and the strong base are both weak, and they don't have much of an affinity for reacting with the water. Okay. Now this is an interesting quirk of the mathematics. If I've added 101 milliliters, that's 10.1 millimoles of hydroxide. Now that means I have negative 0.1 millimoles, which is not possible. We don't do the negative number thing. We just have to realize that what really is happening here is we're changing. The excess reactant is now OH minus the 10.0 millimoles of the H plus. We have 0.1 millimoles of hydroxide ion. We can divide that by 201 milliliters. Milli cancels milli. And again, I have 0.0005 molar, but this case, it's hydroxide. The POH ends up equaling 3.30, and the pH equals 10.70. And that makes sense. 1 milliliter with this huge jump in pH is what I would expect. The same way I had a huge jump right there. And that happens when we're near the equivalence point. Okay, well, we'll tune back in for the next video to look at page number 13. Okay, folks, Morgan here. Welcome back. Another lecture for Tuesday, 3/17. Happy St. Patrick's Day. I'm looking at page 13 of the Ionic Solutions lecture outline. We just finished up talking about a strong titration. Now we're going to go on. We're going to look at a weak acid being titrated with a strong base. We have 20 milliliters of 0.10 molar acetic acid and titrating from the burette with 0.10 molar sodium hydroxide. Now, before this reaction begins, the acetic acid HA breaks up into H plus and A minus. We can do an icebox here. We're starting off with 0.10 molar. We have 0 and 0, minus X plus X plus X, 0.10 minus X, X and X. So our Ka is X squared over 0.10 minus X. And you can look up the Ka acid dissociation constant for acetic acid. It's 1.75 times 10 to the negative fifth. We can approximate this no problem. X is going to equal 0.00132. Okay, sig fig y is probably just the 0.13. That's the H plus, so the pH is equal to about 2.88. Okay, now this is going to be a little bit different than the strong acid, strong base titration because I have HA and I'm going to add OH minus, and that's going to make H2O and some A minus. All right, wait for it. Let's see if this is dawning on you yet. You're going to have HA and A minus both present in the flask all the way up to the equivalence point, which means you're going to have a buffer. So what are we starting with in terms of HA? We have 20.0 milliliters times 0.10 molar, which equals 2.0 millimoles. OH minus, we're adding 2 milliliters times 0.10 molar. That's 0.2 millimoles. That's HA. That's OH minus. That's going to leave me with 1.8 millimoles of HA and 0.2 millimoles of A minus is going to form. All right, so we're going to use the Henderson-Hasselbalch equation. pH equals pKa minus the log of the HA concentration divided by the A minus concentration. And since both of these are going to have the same volumes, we can actually just use the ratio of millimoles. pH equals. Now, the pKa is 4.76 minus the log of 1.8 over 0.2, and when I calculated this, I got 3.81. So the pH went up. That makes sense. Let's look at it for when we have 5.0 milliliters. I have 2.0 millimoles of HA that I'm starting with, and this time 5.0 milliliters times 0.1 molar, and what that's going to give me is 0.5 millimoles of hydroxide, 1.5 millimoles of the HA, and 0.5 millimoles of A minus is going to form. Remember, the hydroxide and the A minus are in a 1-to-1 ratio. So pH equals 4.76 minus the log of 1.5 over 0.5, and that's about 4.28. So the pH is going up, but it is not going up drastically. Now, 10 milliliters of the base. Let's see if we can recognize this. We have 2.0 millimoles of HA minus 10 times 0.1 is 1.0 millimoles of OH minus, which means I have 1.0 millimoles of HA. I have 1.0 millimoles of A minus. The HA and the A minus are present in equal amounts, and we're going to call this the equivalence point. So the pH equals 4.76, because minus the log of 1 over 1 would be equal to 0. So this is the midpoint. This is still just early in the titration, or what we might refer to as the buffer region or buffer zone. Now here, we're getting a lot closer to the equivalence point. The 1.9 comes from taking the 19.0 milliliters and multiplying by the 0.1 molar NaOH. 0.1 millimoles of HA are left. I have 1.9 millimoles of the A minus, and the pH equals 4.76 minus the log of 0.1 over 1.9. And the pH is going up quite a bit at this point. That's 6.04. Now, things are going to change here. I'm recognizing as I have 20 milliliters times 0.1 molar and 20 milliliters times 0.1 molar. I'm at the equivalence point. Okay, welcome back for video number 3 and the final video for today, which is March 17th, 2020. Happy St. Patrick's Day. Morgan with you once again. So page 14 is the page that I asked you to give a try on your own. So we're going to go through these calculations. This time it was a weak base with a strong acid. So before we started, we have ammonia, reacts with water to make ammonium and hydroxide. We do an icebox. We solve for X. We get 0.0017. X is hydroxide, so the pH is 2.75. And the pH 11.25, which makes sense. We're starting off with a base. It should be a pretty high pH. Now, if you add a little bit of HCl to it, which is basically just H+, okay, what ends up happening is we get 5.0 millimoles of ammonia to start with and 0.2 millimoles of the acid to start with. That comes from 0.2 times 25 milliliters. And 2.0 milliliters times 0.1 molar, okay? So we're going to go back into the Henderson-Hasselbalch equation. Ammonium will represent the HA. Ammonia will represent the A minus. Now, Kb for ammonia is 1.6 times 10 to the negative fifth. That's something we can look up. I converted it to Ka, which I actually think is in a table in this lecture outline a few pages back. We get 6.25 times 10 to the negative 10th. So the pKa is 9.20 minus the log of 0.2 over 4.8. We get 10.58. We're in the buffer region. We've added a couple of drops of HCl. We now have both HA and A minus present. Now, after 12.5 milliliters, boom, we have 5.0 minus 1.25. That gives us 3.75 left over of A minus. 1.25 of HA appears. And what we end up with is 9.20 minus the log of 1.25 over 3.75. And that's 9.68. Okay, still in the buffer region. 25 milliliters. That's going to be the midpoint. 5.0 millimoles of A minus, minus 2.5 millimoles of the H plus, which is a 1-to-1 ratio with the HA. We have 2.5, 2.5. The pH is 9.20. So even though we've added 12.5 milliliters, the pH did not change drastically. Less than 0.5 of a pH point. All right, so almost up at the equivalence point. 5.0 minus 4.99 gives us 0.01, 4.99. Plug that into Henderson-Hasselbalch, and we get 6.50. Now that makes sense. It should be getting pretty low when we're getting close to equivalence. At equivalence, the A minus is gone. All we have left over is HA. What we end up with is 5.0 millimoles. Divided by 75 milliliters is 0.066 molar. Classic icebox, solve for X. X is H plus at this point, pH of 5.19. And when we did the whole thing with the salts, making the jokes there about who's your daddy, you have a daddy acid that is a strong acid, and the mother base is a weak base, so the equivalence point should be down in the acidic range. 5.19 is. Then when we go past the equivalence point, just a little bit, 1 milliliter. We're adding straight H plus at this point. The pH is going to shoot down a lot. It's really going to change drastically. And 1 milliliter takes us from 5.2 to 2.9, basically, rounding off. So it took 12.5 milliliters here to go from 9.68 to 9.2. That's buffering. 25 more milliliters, 24.9 to be precise, and it goes from 9.2 to 6.5. Then 1 dose of 0.1 milliliters drops it from 6.5 to 5.19, and 1 milliliter more takes it down to 2.88, which is where it should be. It should be acidic. Okay, so as that stands, that's the end of this lecture outline. And the next lecture outline is going to be thermo. I have given you some videos to watch. So I want to reward those of you that actually sat through and watched this whole video by giving you some extra time on something. I'm going to be posting an extra credit that you can do for grades this week, because there's no way for us to do our typical things for extra credit not being in the classroom. So there's a assignment right now on Khan Academy. I just made it yesterday dealing with all of the acid base stuff, and I put a due date into next week. If you finish all of those videos by Thursday night at midnight, I will give you 10 points of extra credit for the grades that I'm going to turn in on this Friday. Okay? So I'm putting that in here at the end of the video to reward those of you who actually watched the whole thing, and I will post it on Wednesday so that those people that didn't watch this whole video will have 1 day less to complete the assignment. Okay, so that's Morgan here, signing off from Redondo Beach, California. Hoping you're all having a good day. Stay safe, stay healthy, and we'll talk to you again soon.